getting coffee or tea, we're going to get started. Thank you all for being here for our interdisciplinary colloquium. I want to mention, I don't know if you have noticed, but this year we have increased the number and frequency of our interdisciplinary colloquia. We used to have them once a quarter, but by popular demand, I guess, as they say, we're starting to have them more often. Today we have, I have the great pleasure of hosting, we all have the pleasure of hosting Beth Willman. She's going to tell us about LSST, the Large Synoptic Telescope, and the map that's going to produce over a number of years. Beth is now the deputy director of a new organization that's being set up. The acronym is NCOA, NCOA, and I don't remember the full name unless I actually look at it. So the National, oh there it is, okay, the National Center for Optical-Infrared Astronomy, which is being set up to incorporate the National Optical Astronomy Observatory, Gemini Observatory, and LSST together. So our astronomy community is going through this reorganization, and Beth is serving now as the deputy director. In her previous responsibilities, she was the deputy director of the LSST project up until just a few months ago. Going back a few years, not that many years actually back, she did her undergraduate studies at Columbia, PhD studies in astronomy at the University of Washington. Her research interests cover studies of the Milky Way and understanding dark matter by using the Milky Way and the neighborhood, and also studying ultra-faint small galaxies, primarily in the nearby universe because you can't see them that far away. She actually discovered at some point a new class of ultra-low mass galaxies, and the very first member of that class was named after her, and it's known as Willman 1. After her PhD, she became the Clay Fellow at Harvard-Smithsonian Center for Astrophysics. Following that, she was the James Arthur Fellow at NYU, and then became a faculty at Haverford College until 2015, when she was recruited partly by me. I was on the selection committee. She was recruited to become the the deputy director for LSST. Oh boy, this is not good.
You should have some tea.
I'm back. Coffee, I need tea. So after her during her 3 years as deputy director of LSST, she actually led the $700 million proposal for the LSST operations. She's going to tell us about the survey. Right now the telescope is under construction, and you see how it stands right now. She's going to tell us all about it. Right now, as she's starting her work as part of the National Center for Optical-Infrared Astronomy, she's also an associate astronomer at the Stewart Observatory. So it's a great pleasure to have her, and I can't wait to hear more about this magnificent map we're all waiting for. Go ahead.
So thank you for that very generous introduction, Vicky, and thanks to everyone I've had the pleasure of interacting with so far. I've had an absolutely wonderful day here at Northwestern so far, and become really energized by the science conversations I've had with a variety of students, postdocs, as well as faculty members. So I'll say, at dinner last night, one of my colleagues was Susan Vanderlee, who I got to meet from, I think, the Earth and Planetary Sciences Department. And I got to learn for the first time about EarthScope, and she sort of said, you know, I see the title of your talk is the most magnificent map ever made. So why don't we talk about the magnificent map that we're making of the Earth itself and of North America. And it was pretty magnificent sounding, but I stand by this title, despite the conversation we had. So I'm going to start here. This is both a loose outline, and it's a set of points that I aim to make over the course of this talk, and it's the same slide that I'll end on. So I'm not going to talk through this in detail or read these bullet points, but I'll say I'm going to bookend this talk with a little bit of, sort of what is the meaning and role of the work that we all do in the broader context of things beyond just answering physics questions about the universe, which is what drives most of us to do our work. But there's more to it than answering questions about the physics of the universe. Over the course of my talk, I'll keep things at a pretty high level so that it's accessible to folks from other departments or perhaps amateur astronomers or students. And then from time to time, I'll dive in more technical detail on topics relating to LSST, where it is in construction, how are we going to turn the enormous data set into something that a diverse scientific community can do science out of, and what may be the role of this planned National Center for Optical and Infrared Astronomy in enhancing and facilitating cross-coordination between different fields that are in ground-based astronomy itself. Okay, so it's Friday and it's lunchtime. I appreciate all of your time, so I'm going to try to make this sort of fun. And I'm going to begin with a point that I have to say, right, I was one of the first students to use Sloan Digital Sky Survey data for my dissertation, so I was working with maps and making maps to look for slight statistical fluctuations of stars in order to try to discover galaxies that hadn't been seen before. And then I did this during my first postdoc and my second postdoc. And it wasn't until I got to be a faculty member at Haverford College and work with students like Mike Bueno, who I also was privileged to catch up with yesterday, that I really zoomed out a little bit and thought about, well, how do other people engage with the universe and what does this mean? And I gained an appreciation for the fact that, right, for centuries, maps of the sky have really guided human understanding of our place in the universe, and not just our pursuit of physics in the universe, and not just stamp collecting or writing down what the universe happens to look like. And so, of course, for all time, people could look up at the sky, much more so a long time ago than we can now, and see this literally Milky Way that passes through our sky. And it was in 1609 when the first telescope the telescope was first invented, right? That Galileo pointed that telescope up at this Milky Way that you can see with your naked eye in the sky, and wrote this starry messenger writing, and observed that the galaxy is nothing more than a congeries of innumerable stars distributed in clusters. And so back in 1609, that was really the first observation of, what is that Milky Band in its increasing density of stars as we look closer to the plane of our galaxy. And I really loved bringing this starry messenger reading into my introductory astronomy classroom, because it's this collection of fascinating early observations, not just what the Milky Way is made of, but these early observations of Jupiter and the discovery of Jupiter's moons. And this always really struck me as an interesting, again, early example of open data and immediately publishing a new discovery before you fully inventoried and described the system. And here's a sketch that Galileo made of the positions of those point-like sources of light moving back and forth across the face of Jupiter. And as I think about the impact that these observations would have on folks' sense of place in the universe, right? This was the first real observation that objects orbit around something other than the Earth. Took place in, I think maybe this was 1610 that this was published. Is an evolution and thought of the Earth is not uniquely special in the universe. And how many folks are familiar with this image of Earth taken from Voyager 1 back in 1990, right? And so there's a famous Carl Sagan essay, Pale Blue Dot, where he refers to this little dot here as a mote of dust in a sunbeam, right? So when the sun streams in through the window, you see those little floaties. And the Earth looks like a mote of dust from this distant vantage point in our solar system. And I'll offer, for those of you that are unfamiliar with this Pale Blue Dot essay, it's a fantastic read where you can go to YouTube and hear this emotional music and hear Carl Sagan's voice reading over these different images of Earth taken from the outer solar system. And it's an essay inspired by this image that I think a lot of people have found some solace in over the course of our history, over recent events in this country, where people have felt challenged to understand and find their place in the world around us. This Pale Blue Dot, inspired by astronomical images, has really provided that connection point. And I'll confess, and Mike never took this class from me because I left Haverford too soon. I used to show this image and have an audio of Carl Sagan reading the essay at the end of all my introductory classes. And I would sneak out of the room because I would always tear up and it was super awkward, and I couldn't desensitize myself to it, no matter how many times I would show it in the classroom. It was always the case. And so my last historical map that I'll make reference to is another one that I find incredibly striking. This map that the Caroline Herschel and her husband William, or brother William, I believe, made in the late 1800s of the Milky Way by basically assuming all stars had the same intrinsic brightness and then getting some relative distances to the stars that were mapped visually through this telescope. And I don't know if this image is still in Astronomy 101 textbooks today. It was when I was, back when I was a student, and I was a TA for introductory astro classes at the University of Washington, and I just ignored this image. It's like it's boring and it's scraggly, and I don't understand what we're supposed to get from this. What's interesting about it? And it was only, again, when I myself was a professor that I appreciated the beauty of this image, because there's dots there, and it seems that they were very easy to map. But when you think about how far away each of these hand-drawn stars are from each other in reality, right? What is the scale of even just our local universe in the Milky Way, right? If my head is about the size of one of these stars, and what state am I in today? I'm in Chicago, Illinois today. So if my head is the size of one of these stars, the next closest star that's the size of my head, we're in the middle of the country, so it's even past California, or it's past New York City, right? The universe is enormously empty. And so even maps as early as this, and I'm moving through to today, it is an extraordinary feat of human accomplishment that we, as physicists and astronomers, are able to map our natural world in this way out to enormous distances, and to use the physics we study on Earth to draw inferences about the natural world and how it's changed with time. And so that sort of, that inspiration of human accomplishment and building on generations before us is something that has inspired me to move forward in my research and also in my mentoring and teaching of students. And so, just skipping over a couple of decades, I've chosen this animation of the Sloan Digital Sky Survey. There has been about 1 billion objects cataloged by the Sloan Digital Sky Survey. About 1 million galaxy spectra were obtained, which has enabled this three-dimensional fly-through visualization of the SDSS survey over about 1/3 of the sky, where the spectra of the galaxies give us the distances to the galaxies, and then also both the colors and the spectra of galaxies can tell us something about what their color may look like to our eyes in these optical bands. And right, for quite some time, for decades, these surveys have been used to answer questions about the physics of the universe. A lot of people here in CIERA, in the Physics and Astronomy department, are doing just that, using survey data to ask questions about stellar astrophysics and cosmological questions, including a recent Nobel Prize awarded to a team that used supernova survey data to measure dark energy in the universe. And something I find really striking when I look at something like this is it's reminding us that visualization has really become of paramount importance for us reaping the maximum benefits from modern day surveys of the universe, right? So here it's fine, there's spectroscopic data, we have a three-dimensional map, we know some one-dimensional velocity information and color information. Looking ahead to LSST, which I'll quantify soon, and even thinking about the current generation of numerical surveys simulating the history and the future of the universe. How do you explore and ingest the information contained in a numerical simulation with millions and millions of points or pieces of data, and at every location you have information about temperature, density, three-dimensional velocity, position. How do you really walk through that? And I'm no expert in this area, and I've just started to wake up to all of the different techniques. They've been in the air for a while. Way back when I was in grad student, people were talking about visualization caves and different ways to explore data sets. I feel like right now we're really at a crossroads with the volume and velocity of data that I hope to see over the next decade a much deeper exploration of these innovative visualization approaches and closer partnerships between experts in computational science, virtual reality, and astronomy and physics to use these innovative ways of exploration. And so I was at University of Washington a few months ago, and a friend of mine kept saying, "Oh, I've got this virtual reality thing. You've got to see it." Well, that's kind of weird, I don't put this thing on my head, but finally I submitted to what he wanted to show me, and it was extraordinary, right? You sit in a little pod and you fly your pod around, and you've got a glove on, control which dimensions of the simulation you're able to look at, and really go up and explore and look at the distribution of, in this case, the predicted dark matter massive properties in the universe. And so, okay, so SDSS is a major survey, publicly available. There's been other surveys, PanSTARRS, the Dark Energy Survey, at optical wavelengths. I'm going to be very optical biased over the course of this talk. Since then, really, what are we looking ahead to as a community in terms of massive optical surveys? And so this is a Large Synoptic Survey Telescope. And so what is LSST? So it's what you get if you put an optical camera with 6 broadband filters on an 8-meter telescope, and with a field of view the size of 40 full moons. And then we can use this camera to take 1,000 pictures of half of the sky over a 10-year period. So effectively making a movie of the sky in broadband filters that spans 10 years. And so here's an engineering sort of cartoon of the camera itself. We have 6 filters in total that LSST will observe with. 5 at a time can be held within the camera. And that 40 full moon field of view, kind of you hold your arm out at length, and your thumbnail is about the size of 1 full moon. And so imagine 40 of those. It's about a single image that LSST can obtain. And so there's a number of ways you can sort of conceptualize how large this camera is. This 3.2 billion pixel camera that was built at SLAC in collaboration with Brookhaven National Labs. One is that it's the size of a Volkswagen Bug car, and Margot Lopez, an engineer at SLAC, I think she likes corgis a lot. She uses the analogy that 240 corgi dogs can fit inside the body of the LSST telescope. Okay, so 3.2 billion pixels. There's a number of things that are remarkable about this sort of boundary pushing number. So it's 10 square degrees. These 3.2 billion pixels, a requirement driven by the desire for LSST to be sensitive to short-term transient variable events, was that these pixels will be read out in 2 seconds, which is incredible to me. And you know what? Right before I moved to LSST, I used to take students to observe on the 0.9 meter telescope at Kitt Peak National Observatory. And there was a single chip camera that we used to use, and it was perfect for undergraduate observing. It had a 3-minute readout time. And so you take the image, you hang out, you talk about it, you think about what you're going to do next. 3 minutes. This is 3.2 billion pixels in 2 seconds. Another thing, which is not just a cool soundbite, is that to observe a single full resolution LSST image, you would need to cover half a basketball court with HD TVs. And so one thing that, like I said, it's not just a fun soundbite, that I've really been thinking about is, fine, all of this enormous image, this set of images are going to be turned into high-level calibrated data products. People can do science with it, and that's fine. But something that I've learned over the course of being a survey scientist is that it's really dangerous if you completely divorce yourself from putting your eyes on the pixels, right? And so the entire time I was in graduate school, I'm like, oh, I'm just looking for statistical signals, and I have to do everything mathematically, and I can't be going in by hand and looking at things. So I convinced myself of this. So I wasn't really looking at the pixels at all. And it got by okay. I could also, put 1 million stars on my desktop computer and write terrible code and get new science out. It was a different time. But nowadays, fast forward, I got a week of time on the Gemini telescope to observe an interesting, set of new discoveries that were subtle data anomalies in a different survey data set that shall remain nameless, where the photometric flags were inadequate to highlight subtle issues with the data. And it was only when one looked by eye at the individual thumbprints of the individual exposures could you see single pixel glitches that tweaked the colors just enough to make you think you had discovered a new class of objects. And so looking ahead, right, so with the transient facility LSST, you have millions of objects coming down the pipe, and we need to think of very clever ways to find the small number of the most interesting ones to invest our resources in. How do we get around that, right? How do we do that without getting our eyes on the pixels, which is, I think, a big open question that we can learn a lot of lessons about in the current era. And so I won't talk about this in detail. I'll just highlight for interested scientists that there's this overview paper that Joko Obezic has led and updated every few years, which quotes the LSST depths in each of these filters, the mean number of visits, and what is the depth? How faint of a point source can you detect at 5 sigma significance if you stack all of the images together at the end of the survey length, at the survey lifetime? And so this is deeper than an optical dark energy survey, of course, substantially deeper than SDSS, and very complementary to a time domain survey like the Zwicky Transient Facility, which is observing even wider area of the sky at a time, but to far shallower magnitudes. And so the next few slides I took from Andy Connolly, who's faculty at University of Washington and gave a very nice TED Talk a few years ago. And so this visualization here shows a cartoon of LSST mapping the sky, with each circle containing about 10 million galaxies, each single pointing about 10 million galaxies. So this translates to about 20 terabytes of images obtained per day and 15 petabyte database at the end of the survey. If you collect all of the data products, it's about half an exabyte worth of data at the end of the 10-year survey lifetime. And so simulations suggest that we will have 40 billion objects identified in that stack of data at the end of the 10-year survey, roughly equal between stars and galaxies. So for the first time, we'll catalog, is it for the first time? Well, it certainly will be the fact that we'll be cataloging more objects than humans on Earth. And because each one of these 40 billion objects, the location of those objects will be force photometered in all the 1,000 images, there'll be about 40 trillion see what I call these other sources that are measured, each of which will have dozens of pieces of information measured about them. So it'll be quite a complex data set to be observed. And right, fine, you could say, oh yeah, build a large telescope, put a big camera on it, see what comes out the other end. Of course, to get funding for a $1 billion scale project, it needs to be designed around science drivers with quantitative requirements that are shaped to satisfy those science drivers. And so one of the science drivers is dark energy. And each one of the 4 pillars of LSST science was selected not just to be a cutting edge science case with substantial opportunity in the 2020s, but also to push at all of the corners of those technical requirements so that in the middle, a vast range of additional science will be enabled. And so the requirement pushing area of the dark energy science pillar is our understanding of systematic effects. How precisely do we need to know the shapes of point-like sources across the field of view? How precisely do we need to understand the sensitivity across that 3.2 billion pixel focal plane to photons coming in with different wavelengths, for example? And so the construction project is structured to ensure that as components of LSST are being built and then commissioned, that there's impeccable characterization of the system. And our operating plan includes scientists who need to characterize the data and characterize the state of the observatory system as a function of time to ensure that dark energy goals can be met. And I'll say also, LSST is funded, construction is funded by a partnership between the Department of Energy and the National Science Foundation, where this one science pillar is the one that excited the DOE to be a funding partner for construction. And so, of course, and I've had many conversations over the last day about this, these repeated observations of the sky will open up new windows in observing the changing universe that are very complementary to the surveys underway now. Now, of course, again, as folks in this room know, LSST is not optimized for time domain science because it needs to support a large number of different science cases. It's currently the case that there's an open call for white papers for the community to suggest limited specialized cadences that can help increase or maximize the amount of time domain science that LSST can produce. I know that there's at least several people in the department here that have a leading hand in some of those white papers to make recommendations to LSST. And I'll have a couple more animations about that in the future. I'll just highlight one more thing here. In order to pick out these areas that go bump in the night, right, LSST will generate a template of what the static sky looks like from repeated observations early on in commissioning it in the survey, take the difference between those two images to see where the sky has changed. And even when you do that, you expect to have many millions of triggers of places where the sky appears to have changed over the course of the night. And there's a lot of different decisions that need to be made to decide which of those are probably true physical events, or which of those are something funny with the noise or a glitch with the camera. And those approaches to separating out the signal from the noise range from, again, extraordinary understanding of the responsiveness of your focal plane to photons, as well as machine learning techniques that can be used as afterburners to process the potentially detected alerts through. The third pillar, which is on this slide, the third pillar of science is studying the solar system itself. And so not only can you see things changing and how bright they are or what colors they are, or if they disappear altogether, but you can see how relatively nearby objects move back and forth across the sky. And LSST really picks up where Gaia leaves off in terms of the astrometric precision as a function of magnitude, and picks up roughly equivalent to Gaia astrometric precision at the very faintest end of Gaia, and then goes on down to fainter magnitudes with, of course, decreasing astrometric precision. And there's been a lot of attention paid to what LSST might deliver in terms of potentially hazardous asteroids. Of course, right, there's the congressional mandate in terms of cataloging potentially hazardous asteroids that could impact the Earth. LSST will be well placed to, is there a Planet 9? Is there more of these Oumuamuas? I don't know if people are familiar with Oumuamua, which is the first interstellar asteroid to recently have been detected by pan-stars. This provides us an opportunity to observe very close by to us the sorts of remnants of the formation of other stellar systems, which is pretty awesome. And then finally, I think, that's my last animation to click, is the fourth science driver here, which is the Milky Way and the local volume, which is, Vicky highlighted the area that my work focuses on. So this is just some random picture of some random galaxy. It's based on galaxy. I found it on the internet. It's not particularly pretty. And when we think of a galaxy, or you see like the cover of a magazine and it shows you a galaxy, it's something like this. And this part of a galaxy contains, like 90% of the stars, the starlight, and the gas in a galaxy. But right, this is a TC. This is like 0.01% of the volume of a galaxy. And so if I zoom out on that picture and embed it on top of an image of a dark matter simulation of what you may expect the distribution of mass to look like around a Milky Way-like galaxy, it looks something like this. And so the stellar halo, or the dark matter and stellar halo of a galaxy, is the area of a galaxy that I'm particularly interested in, because the long dynamical timescales preserve some information about the initial formation of the galaxy. And it's also the case that galaxies of all masses are expected to contain their own ecosystem of smaller galaxies orbiting them. And that studying this ecosystem of smaller galaxies orbiting them provides a unique way to investigate and measure what happened in the earliest stages of the universe's formation. And I'll say a couple more words about that in a slide or two. I think I lost a slide in there. So I said here the billions, I think it's about 17 billion stars are estimated to be cataloged. 17 billion stars, many of which are in the Milky Way, but not all, estimated to be cataloged by LSST. And one use of this, this is shown for the Sloan Digital Sky Survey. Even though LSST is an imaging-only survey, we can use the colors of stars across those 6 broadband filters to calculate their metallicity, to calculate their iron over hydrogen abundance. And SDSS has done this in a very limited area, roughly an 8 to 10 kiloparsec radius from the center of our galaxy. And that's just limited by, again, the photometric depth. How far away can you see red giant stars and get really precise measurements of their light output in the bluest filters, the U-band filter depth. And with LSST, we expect to be able to make a spatial and metallicity map out to dozens, if not hundreds of kiloparsecs from the center of the galaxy, even just with imaging alone. In addition to that 3-dimensional map of the relatively smoother component of the galaxy, it is known that at least some of these predicted clumps of dark matter halos orbiting around the Milky Way are lit up by dwarf galaxies that reside within them. And so it was the case, let's see, I was a grad student around here, the time that I was a graduate student, there were 11 dwarf galaxies known to be orbiting around the Milky Way. And it's truly remarkable that between the Sloan Digital Sky Survey, the Dark Energy Survey, and a variety of other wide field surveys in between, we went from literally just seeing the tip of the iceberg of what a galaxy is and can be, to realizing that galaxies that are 1/1,000,000th or 1/10,000,000th the luminosity of the Milky Way appear to be the most numerous type of galaxy in the universe. And the only reason astronomers were able to make those discoveries was because of the advent of these wide field uniform digital surveys and multiple filters, right? So SDSS was 54-second exposures on a 2.5-meter telescope, and we about doubled the number of known dwarf galaxies orbiting the Milky Way based on those observations alone. And so I'll give a couple of examples of the types of stellar populations that are used, that are observed in these survey data to show us galaxies that are really at the bottom of the galaxy luminosity function and allow us to observe what the most extremes of galaxy formation look like at the very lowest mass end. And so this object, Virgo 1, was discovered in Hyper-SuPrimeCam survey data. So HSC is a large camera on the Subaru telescope in Hawaii, and it's got about 20% of the 8-ton due of LSST, about 20% of the observing efficiency, so really quite good. And this object, so if you're not familiar, this is a color magnitude diagram. So it shows how blue or red stars are in a particular direction of sky as a function of how faint, or at the top how bright they are. And that green locus there is highlighting the expected distribution in this color and brightness space as a function of magnitude for an old stellar population at a specific distance. I think this was about 100 kiloparsecs away. And so this, you think, oh, what is this? It doesn't look like anything. Each one of these each one of these dots is a single star in the direction of this now called Virgo 1 object. Here's a few red giant stars, and then about 12 main sequence turn-off stars. And those were how this object was detected. So the total luminosity of this object here, it's got an absolute V-band magnitude of about 0. There are single stars in the night sky that are more luminous than the entirety of this galaxy. A lot of the naked eye stars. Of course, it's a huge bias in what we can see with our naked eye. And so deep surveys that allow us to observe these blue and faint main sequence stars are going to reveal an increasing number of these objects that are distant from the Milky Way and appear to be lighting up these predicted dark matter halos around us. And so here this, and I won't get into this even though it's a pet topic, these are star clusters in this part of the diagram, tend to be more compact at a set luminosity, and these are objects that are now classified as dwarf galaxies, relatively more diffuse and less dense at a set luminosity. Okay, so this is something that main sequence turn-off stars can show us. Now we can look at more distant objects, and so this is a super LMC mass object, more than 3 megaparsecs away, NGC 2403, that has been observed through the MADCACH survey that my group and I are working on, which again utilizes a Hyper-SuPrimeCam on Subaru. This object was found actually in a visual inspection of the data and not in an automated approach as we originally were taking. And you can kind of pick out with your eye that there are a few point sources clustered around the center, but these are all pretty bright red giant stars. And so red giant stars let us access slightly more luminous dwarf galaxies farther away in the universe. And this particular object is pretty close to the center of NGC 2403. And so, in order for us to try to measure the dwarf galaxy populations around Magellanic galaxies, Magellanic massed galaxies in the local volume, semester after semester there's observing proposals, going to Hawaii to observe on the telescope many times. But the era of LSST, well, we will have for free over half of the sky red giant branch stars observed out to up to 6 megaparsec distances. Okay, so it will really be a revolution in the way these sorts of near-field cosmology studies can be done. And when I say near-field cosmology, I mean we can study nearby objects in exquisite detail to get a picture of their current state and their formation history, and that really complements looking at ever-increasing distances away and stitching together the average picture of the universe's formation and evolution. And so near field cosmology has really had a huge coming of age since I was a graduate student, and again, enabled by these massive data sets and also complemented by space-based higher resolution observations that let us study these objects, their history, and how they could have been impacted. I know I'm looking ahead, I'm really excited about going from an era where, wow, we know these objects exist. There's an enormous number of galaxies with just thousands to tens of thousands of solar luminosities, to then saying, why did they all stop forming stars 10 billion years ago? Was it reionization? Was it other galaxy formation physics or not? And so I'm really looking ahead to an era where we started looking for these things because we wanted to understand dark matter. We found them and we realized we have more to learn about galaxy formation before we can start learning about dark matter. And then I hope for the next 5 or 10 years, we can learn those things about galaxy formation and come out the other end to really understand the ways in which these are more or less biased tracers of dark matter that exists in the nearby universe. Okay. So I'll put that pet topic aside for now. Okay, so what are these images going to look like? So here's a Sun Digital Sky Survey image. I included that just because it's the ground foundation for a lot of us in terms of what's the most accessible and wide field optical survey right now. And then this is a Hypersweep PrimeCam image that was selected and stacked to be roughly equivalent to a stacked LSST image at the end of the survey. And there's two things to notice about this LSST-like image. The first is obvious, just the extraordinary richness of information and structure that we'll be able to observe at LSST's depths. But another one is more of a data management issue, which is, even if you look up close at this image, there aren't very many sky pixels in that image, right? The point spread functions of stars overlap with the extended distribution of the light coming from galaxies. And so it is not a very easy problem to solve, to write a pipeline that turns these images into calibrated positions, magnitudes, and colors that scientists can use to do their science because of all of the overlap between the flux of the sources that are present in these images. And so one thing that Tony Tyson, Steve Kahn, and other senior scientists that have been associated with LSST since the late 90s were incredibly smart to do was to recognize that the software challenge of turning images into data products and then the enormity of delivering those data products in a way that the community can use had to be baked in from the beginning, right? And so of about the $700 million construction project, well over $100 million is for the data management system. In terms of the operations cost, of the $60 million and then year dollars operations cost, about a third of that is related to pushing out well-characterized data to a worldwide community of users. It is not inexpensive to push out the data in this way. And something that I've heard Tony Tyson say, right, the observatory itself is kind of like the world's largest peripheral. Right? It's this data management system that is absolutely required in order to enable the science that the agencies, the taxpayers, frankly, paid to build LST to accomplish. Okay, I've referred to the observing strategy in passing. Here's that blue band showing about half the sky that we expect to be observed roughly 1,000 times over the 10-year survey lifetime, potentially with more limited visits to the plane of the solar system, to the southern celestial pole, and then also to the galactic plane. Now, given that the technical requirements of LSST have been set in stone for quite some time, the hardware in the system has largely been built. There's only a couple of knobs you have left to turn to maximize the science coming out. And the biggest one is the observing strategy. How do you tell the telescope where to point when? Right? And it's not a human sitting at the telescope thinking, oh, you should point here now. Right? It's a collaboration with software engineers who develop a scheduler that is the brains of the telescope, that tells the telescope where to point when. Where have you observed before? Where do you need to observe in the future? What is the weather like? What has the weather been like in the recent past? What is the image quality like? So what filter should you be putting on the camera right now? And so the community has been invited to give input into this observing strategy. So LSST itself is not making those judgment calls on how to do different types of science. And so this is just one example of a simulated survey. And you can see those those fields getting populated across the sky, and it hops around a little bit. The operations plan is such that the observing strategy will be continued to be evaluated for whether it's meeting the projected goals and the efficiency expected, and there will be a community panel of some sorts implemented during operations itself to advise LSST on how well the observing strategy is accomplishing the goals, the scientific goals. In particular, I mentioned some folks here are involved with writing white papers to recommend to LSST ways that they could enhance science with the observing strategy. And one particular example is by allowing target of opportunity follow-up for gravitational wave events. So I've already alluded to the fact that LSST is really a comprehensive system. People think of an observatory, they picture a telescope on a mountain, and that's it, and that's where the action happens. They picture people going there to observe, and that is not what LSST is all about. It took a lot of the time that I invested in developing the operations plan to convince our advisory boards and the agencies that the amount of money we were saying is necessary to operate LSST to meet the science goals it was sold on requires a substantially larger operating budget than other 8-meter telescopes because of this petascale data management system and the need to very carefully characterize those images. In addition, I think LSST is the only NSF MREFCs, the construction funding line, project to be given money to construct an EPO program in advance of operating. Right? You can't do EPO during a construction project, but you can build the infrastructure for your education and public outreach project. And so LSST has a very data science forward-looking EPO plan. And so I'll hop pretty quickly through the next set of slides because I've already said a lot of these numbers here. I'll highlight this alert stream is expected to push out alerts within 60 seconds of an observation taking place. And so an overused phrase that I will continue to overuse, it truly is a fire hose of transient alert events. And I'll show a schematic in a few slides of how they might go from LSST out to the user community. This alert stream itself is world public. It does not require data rights. On an annual basis, there will be a static catalog pushed out to the user community. And the data production is transparent. You can go on GitHub right now and look at the most up-to-date set of software that's using to turn precursor images, both simulated and hyperspeed prime-cam images, into calibrated data products. And there's people in science collaborations now who are using those early versions of the pipeline for their own science. In particular, actually, there's a partnership between the team building the alert stream software, both the difference imaging and the distribution software, that's partnering with the Zwicky Transient facility to do early testing of that alert distribution software. And I refer to data rights. All US and Chilean scientists, as well as a set of named international contributors, have LSST data rights. And as Vicky is aware, there's a process underway to develop more concrete data rights and access policies for LSST. Okay, so what is the mechanism by which these data products will be distributed to folks with data rights? We're kind of, at least in optical astronomy, we're almost in an era where the commodity isn't really data rights as much as it is data access. Because when you have huge numbers of terabytes of data to interact with, there's super users that can pull that over and put it on a big cluster that you may have at your well-funded institution. But overall, it's really the access to the data. And so there's going to be a tiered science platform. It's already under development that will enable folks to connect in every way from, you go to a website and you click on some radio buttons and you can get an image of the sky or a finding chart. So using, Jupyter Lab, notebooks, and then more advanced users can connect via web APIs, collaborate with colleagues around the world. And in all these cases, LSST will be providing computing resources next to the data. Again, because we're not in an era anymore where your average user can accomplish all of their scientific goals by pulling a limited set of objects over to their desktop computer and running code on them. And these sorts of considerations go far beyond LSST. And it's really the software and data infrastructure are at least as important to science in the era ahead. And this is for a wide range of experiments. Again, I learned about EarthScope the other day. There's the Committee on Science, Engineering, Medicine, and Public Policy at the National Academies next week is having a panel to study How can the medical field learn from these distributed experiments? How do we connect metadata to how the experiments were run, and then push the data out to a broader set of scientists to benefit from them? And there's a number of parallel efforts right now, particularly in astrophysics, that are investigating and trying to quantify, with an eye on the upcoming decadal survey, what sorts of infrastructure is necessary for us to accomplish our science goals in the 2020. There's a Cobley-funded series of workshops that AURA has been implementing. There's this cyber infrastructure, multi-messenger astronomy effort that NSF is encouraging. I think there's a conference or workshop at IPAC in December that's trying to drill down into these questions as well. And I think the real elephant in the room, and again, folks here know even more than I do how big that elephant may be, is how do we actually handle the alert stream? And I sort of picture, are we just going to turn on the faucet and have all this water running down the sink? How can you conceivably handle, millions of alerts per night? And as the survey goes on, the sky will be more well characterized, and you can separate out the variable, the predictably variable events. And so here's an image from an SPIE proceeding led by Rachel Street that is visualizing something. It's on the Astronomy Observational Event Network, I think it's something like this, where you have these time domain surveys with alerts that go through brokers, and with targets that can be selected to satisfy a set of criteria you're interested in. You can select out for types of supernova you might like, and the user could access those sources through a target observation manager. And so, for example, Las Cumbres Observatory has been working on and has already deployed a target observation manager. And so astronomers at the observatory partner with software engineers to develop a target observation manager that can pull in information, or that can connect with, I should say, event brokers across the world to allow users to pull their targets out. And then again, partner with software engineers. This could be a Las Cumbres scheduler or otherwise. So the user can say, I'm interested in these targets. I have dedicated TOO time on these facilities, and then the scheduler could automatically push the observations out to the different observatories. Right? I have this looking like a nice set cartoon. It's very conceptual and under development, but interesting thing is that Gemini and SOAR telescopes have stepped up to the table to partner and to try to strengthen this ground-based network for time domain astronomy. I'll say just a couple of words here about the National Center for Optical-Infrared Astronomy. So right now we're working very hard in order to get the NSF's green light to launch this integrated center that will integrate the operations of LSST, Gemini, and NOAO within a single organizational framework. And here you have images, including LSST, of the observatories, as well as a picture of numbers scattered on the floor, which is intended to evoke one of the 4 initial programmatic pillars of NCOA, which is currently within NOAO, which is the Community Science and Data Center. And this pillar of NOAO and future NCOA is really aimed to provide support for data-intensive astronomy by a broad user community, trying to tackle that challenge of how do people get the skills necessary to do astronomy in this new way, which isn't just going to the telescope. And then also, community advocacy and optimization for the US OIR system overall, and being that central clearinghouse, the telescope allocation of all of these resources. Thinking about some of these policy questions. How might the TAC process need to change to accommodate the time domain dimension of what LSST and ZTF are bringing to us? And I'll just put a little highlight here. So you can imagine, looking ahead to the future, if there's going to be a US ELT program, right, the NSF is looking at something like NCOA as, is our national centerpiece for negotiating on the international level with billion-dollar projects of the future. Before, if you had Gemini and NOAO and LSST all stood up separately with funding coming from the NSF, it was less clear where do you go to centralize your efforts to negotiate something like this. And there's already sort of an initial cooperation between TMT and GMT that's being shepherded by NOAO right now. And I'll just make a couple of final points. And so the short attention I'll give to this by no means is proportional to how much I care about this topic. Again, so I'll bookend, taking us out of how we can use these remarkable surveys to learn about physics to reminding us of the connections outward. And I feel a strong commitment to the open access to well-curated data sets for a lot of reasons. One is that's how you actually maximize science. And the way that you maximize science, or a way you maximize science, is to just increase STEM participation, whether it's in the field or adjacent to the field itself. And two examples of this increased participation is simply putting cutting-edge research into the hands of scientists at all types of institutions. Right, at Haverford College, I could do all this great research because we were using Sloan Digital Sky Survey data, which was very accessible to anyone with an internet connection. And then it provides an easy opportunity to bring research-based inquiry into the classroom, from high school up to graduate school. And, you know, LSST is the potential to really hit the curricula, to hit the classroom from everything from, you know, computer science, astronomy, physics, statistics, and I'm so focused in almost a religious-like way of the role that these large data sets can play at the university education level. Because, right, the fact is that a very high fraction of all college-educated people in the United States go through some introductory level astronomy, physics, computer science class, or statistics class. Right, and there's different reasons that we all like to bring this research-like inquiry into our classroom. Right, some of us want to get the next students hooked in so they go off to graduate school. Some people just want to excite and empower students to have critical thinking skills, to be excited that the physical world is knowable and understandable, and it's something that's worth investing taxpayer dollars in. Right? And there's hundreds of thousands of students a year that go through one of these courses, and I would like to see a future where every introductory physics and astronomy textbook connects with LSST data and makes it easy for faculty members who maybe aren't as comfortable interacting with survey data to bring that inquiry into their classroom. I'll just say one point on this slide, which is that SDSS, rewarded by its open access and low barrier for entry, has an extraordinary publication rate. And in a study that was referred to as the Elmgreen report, sort of a state of how well are we doing in implementing the 2010 decadal survey, in 2014, there were an average of 600 papers a year utilizing SDSS data. And that number of papers a year was on par with HST and exceeded that of Gemini and Magellan, which were, you know, far larger light bucket gathering machines. And the number of papers doesn't equal scientific impact in a seamless way, but it's one metric by which you can immediately see that open access has impacted scientific output. And even for HST itself, which has substantially improved and enhanced the accessibility of its archival data, more than half of HST papers are coming from the archival data versus being written by the original PIs. And so the very last point here that I'll make is, well, why do all this? Why do we care about more inclusion, broadening the participation of people in STEM fields? And right, I mean, there's a lot of reasons. This is sort of the business case on the slide. I mean, it's the right thing to do. That's what I personally believe. Right? But even if you don't naturally think, well, it's just the right thing to do, there's a business case. We have to make science increasingly inclusive, and I believe open data is a way to do that. But right, pushing scientific boundaries is hard. We're all working on really hard questions, and doing that in the most excellent and efficient way possible requires inclusion, right? If we're not welcoming of people from a wide range of backgrounds and with different communication styles, we're not benefiting from the sort of breadth of creativity and knowledge that we could be bringing into our scientific investigations. By the late 2020s, the college-age population will no longer be majority white. That is the reality of it. So the business case is, if you want to bring the best people into the field and you want to take advantage of everyone's perspectives, we have to find a way to be appealing to a broad and diverse range of the population. And something that I feel strongly about, I think maybe more strongly than others, I think it's really humbling and amazing that people work really hard and that everybody, no matter who you are, pays taxes. And we get a little bit of that tax money for what we do funded by the government. And we owe it to the taxpayers to be inclusive of all types of folks. I owe it to taxpayers to be inclusive of their daughters and sons in the scientific investigations that we do. And so again, there's the business case, there's the obligation to where our funding comes from, as well as it's just the right thing to do. It's what we need to do for great science. So I'm going to end here with the same set of points that I started with. And we sort of hopped and skipped through these over the course of the talk. And thank you very much for coming, and again, skipping your lunch hour, postponing it to be here today.
exciting and inspiring talk, and I'm sure you'll be happy to take some questions. So let's open it. Please go ahead.
You said that the readout is going to be 2 seconds.
Yes.
How long do you expect typical exposures to be? And will you, in standard operating mode, be taking many exposures on the same field with the same filter? And what problems do you have at bright magnitudes?
Very good. So the exposures are a single visit, a single pointing in the sky, is expected to be observed as a combination of 2 15-second exposures with a 2-second readout each. The settle and slew time on average, I think, is about 7 to 12 seconds for assuming a relatively nearby pointing, but you can get the average from those simulated observing strategies. And then the last bit of your question was?
Bright object.
The saturation magnitude. Yeah, so the saturation magnitude, I forget off the top of my head, is probably something like 17th magnitude in the center of the optical spectrum. And there's been a lot of suggestions, as you might guess, of during the commissioning period doing a 1-second survey of the sky in order to extend the magnitude range that LSST, that we have LSST band observations of.
Thank
you.
Aguilar?
Yeah, thank you for the talk. You mentioned there'll be a reference mass, right? And then, so will there be some differential acquisition of the data? And then will some of the machine learning be done on the telescope, or is it all post-processing?
Yeah, so I'll answer that in 2 bits. Yeah, there'll be a template map generated, and there's currently different models, but no set design on exactly how that or when the full template will be designed. Of course, the commissioning phase will be an opportunity to begin making that template. And depending on how long there ends up being to map the entirety of the footprint during the commissioning phase, you know, the LSST hopes to begin operations with at least a partial template generated already. In terms of the potential role of machine learning afterburners, my understanding is that the alert processing team is really focusing their core algorithms on avoiding machine learning afterburners and instead focusing on understanding the effect that, you know, subtle correlations in the noise in the image that are caused by, you know, convolving the image with a point spread function, to focus on understanding that correlated noise as a way to reject false positives and to stay away from machine learning afterburners for now to avoid inadvertently taking any decisions or implementing any choices that could eliminate those rare and extraordinary events. So I might guess that the community would be more hands-on on using that sort of after processing, depending on their interest.
Please go ahead.
So, did you have collaboration on the your software data processing stack with the groups that were involved with the LHC? Because they have huge data processing. Is there a lot of overlap there?
Yeah, so the short answer to that question is no. There hasn't been coordination with the LHC group, and we're a bit different in that my understanding is that the LHC team has such an enormous data flux that they have to let data fall on the floor. And LSST is within that envelope such that we can actually keep and host all of the data, so those sorts of decisions don't have to be made like the LHC team is making it. The sorts of experiments that LSST's team has connected with are, so the current head of data management came from leading the Gaia software development team and coordinating with other groups across Europe. And so that sort of experience in developing large production at scale software efforts is where LSST has drawn its connections with.
And did you break new ground on the scheduling side? I mean, that seems like a pretty complex task.
It's interesting to hear you say that. There's a variety of perspectives on how complex the task is, as you can imagine, and a variety of perspectives on what it looks like to finish the scheduler. And so I will not say that we have broken new ground in terms of the scheduling algorithm, but it's the most mature scheduling algorithm that I'm aware of. So I guess maybe that is breaking new ground if it's more mature than other surveys.
Thank you.
I have one question on the dynamic range. So the 17th magnitude was the saturation magnitude, and on the other side, was it 24 or something? 24?
Yes. Yes.
Okay. There was another one, yes?
What is the expected lifetime of the LSST project? And during that time, I know this will vary depending on the observing strategy, but how many times would you expect any particular spot to be revisited?
Very good. So the survey length that was planned for when speccing out the requirements, for example, for the sensors and other aspects of the system, was a 10-year survey. And the agencies have committed, and the international partners have committed to funding that for 10 years. The number, you asked about the number of visits, yes. And so across all 6 filters, every spot in the wide footprint area is expected to be visited about 1,000 times. And a typical filter may be 150 times in that specific filter. So sort of on average, if you were evenly observing the sky with time, it'd be revisited about once every 3 days.
Funding aside, how long could the project continue just based on the apparatus that you have?
That's a great question. I was thinking that in my head as I was answering your question because, of course, people now are talking about, well, what might it make sense to do with LSST after the survey's over in 2032? Do we expect the sensors to be operating with a high enough efficiency to still be functional and make it worth it at that time? And I think, you know, of course, if you have a 10-year requirement, it's probably more like 12 years is the, the median, the min and the max. Probably about 12 years. I'm very interested, as I was talking to some folks here about, I'd be very interested to hear from the transient community about how LSST might be deployed in an innovative way after the 10-year survey end to probe new ground in the time domain, right? Because it's not optimized for time domain right now, but I would have to think by the time that we're in the 2030s, the ground-based system will have developed enough and will have learned enough about time domain science to really be able to push boundaries in the time domain with innovative cadences and innovative ways of implementing the machine. But I think it's, you know, as you're suggesting, it does not have an infinite lifetime without refurbishment. Please.
In your schema, you had these sort of data brokers, and most of them seem to be academic institutions. Is it possible that companies, you think, would jump in? Like, this seems kind of like a Twitter feed. Like, your people enriching it with like hashtags making it queryable. Do you think there'd ever be like a Google LSST sort of feed that goes through?
But if you can repeat the question, I think it wasn't heard all the way.
Yes, so the question was, or the observation was made that it seems that it's primarily university partners who are interested in developing event brokers to process the alert stream. But what about the for-profit world? What about a Google broker? Is there interest in that? I'm not aware of any actively expressed interest, but it's a very interesting question, and there have certainly been conversations about whether aspects of the data stream can be commodified in one way or another. But yeah, I haven't participated in conversations about that.
Any other questions? Okay, let's thank our speaker again.